Okay, for the subtopic of this course, of this topic, today's topic is number satu, kita nak you need to know what's the classification of modeling, types and structures of equation, conditional structures, parameters, and stochastic. Apa maksud stochastic yang ditulis kat sini? Okay, sebelum tu saya nak tanya, saya tahu maling awak buat fraction integration. Bukan fraction derivative kan, fraction integration.
Ya, betul.
Okay, fraction integration. Nat buat apa?
Planning to do under cryptography.
Oh, okay, cryptography. Okay, so setakat ni tak ada apa ni? Tak ada supervisor, bukan. Awak dah ada supervisor kan?
Belum.
Belum ada. First sem ke?
Second sem lah ya ni.
Second sem. So ni awak buy apa? Apa ni master
coursework.
By ni coursework. Okay. Tak apa. Alright. So tak ada masalah lah. Dalam sini. So maksudnya awak kena secara general awak kena tahu lah apa modeling tu, tak perlu tahu spesifik. Okay. Modeling. What's the definition of modeling? Modeling is a presentation of systems that allows for investigation of the properties of the system. So you want to investigate the properties of the system, and in some cases, prediction of future outcomes. And in modeling, it always requires simplification. You cannot take every factors and then put it into one modeling. It's quite impossible to do that. So in mathematical modeling, this is where we put mathematical equations to describe a system, and this will mimic the reality of the physical world using the language of mathematics. Contoh, for example, when the DG, Director General from bukan menteri, director, Tan Sri Hisham tu dia punya jawatan dia apa? Ketua Direktor Kesihatan kan, betul tak? Betul, dia cakap apa? Dia cakap we need to make sure that R0 is less than 1. Dia selalu cakap macam tu. Kenapa dia cakap macam tu? Sebab bila R0, yang tu guna stochastic by the way, when R0 is bigger than 1, the projected spread of COVID is exponential. Dia akan exponent. Spread of COVID will be exponential if R0 is bigger than 1. So benda tu daripada modeling sebenarnya. Statistical modeling. So it will try to predict the future outcomes. Usually, stochastic boleh, deterministic pun boleh juga. Okay, why we model? Because models provide a framework for conceptualizing our ideas and about the behavior of a particular system. And it also allows us to find structure in complex system and to investigate how different factor interacts. For example, for disease, for example, how does when people are spreading, macam mana kalau orang tu pergi ke sini, pergi ke sana ke sini, macam mana benda tu, faktor tu boleh interact, and then how is that going to affect the data of your study. So, dan contoh yang lain, contoh yang paling mudah, gravitational force. Gravitational force, if you put, kalau kita letak TV, kalau kita jatuhkan TV dengan duit shilling daripada bumbung, kenapa dia punya dua-dua tu akan jatuh pada masa yang sama. So you can see that there are different factors and how they are interacting with each other. Saya boleh bagi banyak contoh, nanti kita akan pergi ke satu-satu itulah. Okay, and models can play an important role in informing policies. For example, you need to provide understanding of underlying causes for a complex phenomenon. You can also use it because you want to predict the future. and by predicting the impact of intervention. For example, contoh, macam yang kita alami sekarang ni, pandemik. Kenapa kita tak boleh pergi, kenapa kita disekat dari segi pergerakan? Kenapa kita buat macam ni? So that is policies that you need to follow. Why? Because if you don't do this, something will happen. So sebab tu, contoh yang lain. Kenapa kita kalau kita naik kapal terbang, okay? Kenapa kapal terbang tu didesign dia macam tu? Dia ada sebab. Kenapa kapal terbang fighter jet is different than passenger jet? Why? Why dia punya design tu lain? Sebab tu dia they provide the policies or the phenomenon, the causes of that phenomenon. Okay. Now so why mathematics? You can have many kind of modeling. So, but in this case, particularly, why we are using mathematics modeling? Sebab mathematics is a precise language. It doesn't say, if you say it's 0, it is 0. It doesn't stray away from that. It is also a concise language and also universal. Anybody can understand it. It is an old but trendy language. Hold on a second, saya ada panggilan sebentar. So mathematics is precise, concise, universal. Anybody can understand it, even though you don't understand the language. I mean the word language, but you can understand the numbers. It is old but trendy language. As you can see, that it's really old language. And also the most thing that why we use mathematics is because computers understand mathematics better, understand it best. So then we can use computer. You don't have to use hand calculation anymore. Okay. And why mathematical model? So just now tadi kenapa kita guna matematik, and now why mathematical model? Mathematics synthesize result for many and different experiments. So contohnya orang kimia buat eksperimen lain, orang fizik buat eksperimen lain, orang bio dan macam-macam eksperimen. Tapi matematik dia synthesize the results of those experiments. Experiment they focus on specific aspect. And it's kind of fragment understanding. Yang ni faham macam ni, yang ni faham sikit, yang ni faham sikit. And then it is often hard to infer how the system functions as a whole. So mathematics can be used to unravel the unobservable. And also mathematical model are not bound by physical traits. Apa maksudnya? So saya tanya yang last sekali, yang mungkin yang 1, 2, 3 saya dah explain tadi. Yang last sekali, apa pendapat awak? Kalau saya tanya, mathematical models are not bound by physical traits. Apa yang faham daripada kat sini? Boleh ni ke? Okay, Nat, Malin, dua orang ni saya mudah sikit nak observe. Dua orang tak boleh susah sangat. Ada orang ke tak ada ni?
Ada doktor.
Ada. What do you understand from the last statement? Mathematical models are not bound by physical traits.
For example, force mungkin dia tak ni lah kot, doktor. By physical traits macam contoh Newton's law for the force, the surface area doesn't affect the formula lah. I think macam tu lah doktor.
Okey, sebenarnya bukan itu yang dia bukan tu yang ayat ni maksudkan. Okey, ayat ni maksud apa dia? Contoh saya bagi. For example, in our physical science, is it possible to have a negative time? Impossible, right? Physical science in our, yeah, you cannot possible. But in mathematics, you can put a minus sign because why? It's just a formula. You can just put it and then you can get the answer. It can be stable, it can be unstable, but still you can put the negative sign. The same thing. That is for time. Another example. You can put a negative pressure. Pressure is always positive because if you put something pressure, like not negative pressure, excuse me for that. Zero pressure. Yes, zero pressure. So zero pressure in our Earth, in this world, it's impossible. So, but you can put the zero P. Let's say we use P for pressure equals to 0 in your calculation. So it's not bounded, meaning that you can change the value of the variables that you are interested, and it doesn't have to obey the physical law. It doesn't have to obey the physical law. It can be impossible. Yes, yes. It can go to the impossible physical number or value, something like that. But that can also be what you call it a disadvantage for mathematical model, because some mathematical model, for example, some engineers, when they try to solve something and they get the result that is unphysical, and they just discard that modeling. It can be something like that. I can give you one example. Let's say because I'm using, my field is fluid dynamics, computational fluid dynamics, and I saw, let's say, nanofluids. So nanofluids, when you read some of the papers from nanofluids, what you can get is there are two solutions. One is stable and the other is unstable. So is the stable one is physical? They don't know. Is this unstable one physical? They also don't know. So it can be both physical, it can be both non-physical. So it's not bound by physical traits. So you can just put anything and then just plug in the numbers and then see the results. So that's what I meant by the last sentence. All right, now let's look at the next one. Why we use? Because I have said just now, because we have so many experiments and they didn't connect with each other. So mathematics is used to combine the fragmented information into a comprehensive framework. So that's why we use mathematics. That's why physics, for those who study physics, they need to use mathematics. For those who study chemistry, any science or any technology, engineering, they need to use mathematical model, because it's just you can combine the information into one comprehensive framework. Then it is also used to determine the relationship between the physical traits and also the observable traits. So something that you can observe and something that is physical. And you can also test the hypotheses that are difficult to test in empirical studies. So what is empirical study? We can talk about that later on, empirical studies. So this is like experimental. Okay. So kalau kita tak, contoh yang paling mudah, boleh tak kita nak test suhu apa, temperature for sun? Tak boleh. That is impossible. To see the melting point of a iron or something using the temperature of sun. So that is impossible. But you can plug in the value of the temperature inside your equation. You can also use mathematical model to predict and then generate new hypotheses for future testing. And you can also assist with decision making by exploring what if scenarios. So this is another example of advantage of mathematical model. So if you say that we have negative zero pressure, you can just put the zero pressure, even though it is unphysical. But the thing is, you can just plug in and then it says, what if the pressure is zero? What is going to happen to the system? What if we go back in time? So at negative t, so what's going to happen? So this is the what if scenarios, something that is it's hard to do experimentally. Okay, now this is very important. Mathematical model complements, it's just a complement, dia melengkapkan but does not replace theories and experiment. So kita jangan apa ni, kita tak boleh nak apa ni nak kata macam bukan banggakan sangat. You cannot say this is the absolute truth, the absolute solution. No, you cannot, because it doesn't replace theories and experiments. And also I want to say that a mathematical model is also usually based on experiments. Theories also based on experiments. If you go and find a book about history of aerodynamic, you can see that many of the design of the aeroplane is coming from the experiments. It hardly came from the theories, because all the theories are wrong. Because when you read that book, History of Aerodynamics by John D. Anderson, and try to read that, and some of the older theories are wrong, and they need to use experiment, and then they claim a new theory and they create a mathematical modeling. So number one, experiment, and then theories, and then modeling. But you cannot replace experiment. That is important things. Now, how about simulation? Simulation is like a experiment, but it's not. It's part of the mathematical modeling, but it's not the sole mathematical modeling. So if you create a mathematical modeling, usually we have simulation, and we need to test all the situation that to predict the future, to give some new input to the physical behavior. Okay, so we have 6 different types of classification of modeling. Number 1, we have empiric versus mechanistic. And these six classification of modeling is coming and actually from two different categories of modeling. So I will let you know what I mean by that. Okay, and then deterministic versus stochastic, discrete versus continuous, system versus molecular, static versus dynamic, linear versus non-linear. So you can see this one, these 4 can be included in this case or in this case. Okay, and the bigger part of modeling is these 2, deterministic versus stochastic. Deterministic, what does it mean by that? I think we have explanation right here. Okay, okay, let's go to this one first. Deterministic versus stochastic, because this is the big picture of the classification of modeling. Okay, deterministic, what does it mean by that? This is assuming that the outcome is precisely determined by the model inputs and relationship, and you ignore all the random variation. You determine of something. A given input always produces the same output. So this looks like something that is based from theory. because, for example, you say that a car, you cannot, let's say, for example, you cannot drive faster during the rain. You cannot drive fast more than 80 km/h during the rain. Why? Because this. So that is from your, either from your experiment or from your experience. So that is the theory of that. However, stochastic, this modeling incorporate elements of randomness. The key word right here for stochastic is randomness. So it uses a range of values for the model variables in form of probability distribution. The same input produces an ensemble of output. So the same input, it will give you a number of outputs. So a lot of outputs. It's different. For example, if let's say a normal, usual example is rolling a dice, something. And deterministic example is your forces, force or friction, velocity, something that is related to theory or physical science. You can also have, for example, have hybrid kind of classification of your modeling. What does it mean by that? So you can say that for individual, for a small number, for individual, it's going to be deterministic. For example, for one person, it's deterministic because that is just one person. So there's no random variation for one person. But for population is going to be statistic. So one person is different than the other person. Some people may have been positive in COVID-19, but they are going to have a different symptoms. So that's why the randomness is the elements of the stochastic, and it comes from this. So usually this one is what? This one is statistic. Yeah, you can. Okay, so that is the big picture of the classification of modeling. Now let us go back and see the differences between empirical versus mechanistic. Okay, what does it mean by empiric modeling? Empirical modeling is when you have no prior knowledge of the underlying system. You are driven by data. This modeling is driven by data. And then the starting point is from the data obtained from empirical studies, from your experiment or something. And your aim is to determine patterns and relationship between the data. So you have no prior knowledge, and you make some, let's say, a survey or something, and then from that survey you obtain the data, and then you determine the patterns of the study. However, mechanistic, the difference is that you have some prior knowledge, prior understanding of the system. For example, let us say F equals to ma. F equals to ma is just force, acceleration. You can have some pressure and temperature, heat or something like that. So anything that is related to the physical system usually is mechanistic. This is hypothesis-driven modeling. So it's not from the data modeling. Starting point is from the specific phenomena you observe from the data, and data is used to validate the model. The data that you get from the experiment for the mechanistic modeling is used to validate the model. And the aim of this mechanistic modeling is to provide understanding of some phenomena. So when something happened, okay, now because you already have your knowledge and then something happened, then it will help you to understand that behavior. So in other words, empirical it's more stochastic. and mechanistic is more towards deterministic, which is based on the primates. All right. Okay, example. This is from the book of History of Aerodynamics. So what does it say? What does it say about the Wright brothers? The Wright brothers discarded the Newton sign squared law. So what they read the Newton sign squared law and then they follow the theory, but when they do some experiment, it seems that this Newton's a big name, but Newton's is also have a mistake as well. And they see that Newton make a mistake, so they just threw it to the theory from the Newtons, and then they create their own theory based on their experiment. So in this case, what Wright brothers is doing is the empirical study. They have prior knowledge from the Newton's theory, but it seems like deterministic at first. But when the data doesn't support their theories, they discard it, and then they use their empirical modeling, collect the data, and then they create the theories from the data. Okay, now the second example, food expiry date. Does it really expire on the date it was printed? Have you tried an expired food? Meaning that on the food that is tempered, the expiry date on the label or package, have you tried past the expiry date? Siapa dah try? Awak dah try ke?
Yes.
Try makan? Pernah makan?
I did,
Pernah?
Doctor.
Tak pernah? Okay.
I did.
Ada. Saya pernah. Saya tengok okay dah habis. Tapi sebenarnya tak ada masalah pun. Macam selalunya saya roti gardenia. Macam selagi dia tak keluar putih tu tak ada masalah. So it doesn't really expire on the date it was printed. Roti kan. So in that case, kenapa? So why they say the expiry date is today, but you can still eat it tomorrow? Sebab by their deterministic study. So this is quite deterministic because they understand the behavior of what do you call the bacteria or something like that. So this is more deterministic. So they determine based on previous knowledge or data that they have, and this is more not deterministic. This is more mechanistic, and this is more empiric. Okay. Okay. Kenapa ada gambar apa ni? Ada gambar apa nama saya lupa dia punya ni. Saya lupa nama dia punya stealth, tak salah saya. Stealth. Stealth ni apa? Dia kapal terbang yang supersonic jet. Okay. So that's why, as saya kata tadi, why this jet is different than the passenger jet. Why this jet is different? Because this is a supersonic jet. So supersonic jet is moving at faster than speed of sound. If you move something, if you're moving faster than speed of sound, then your design of the airplane is going to be different. Because why? Because it is based on the theory that about shock wave and so on. And also, if you watch the movie, I forgot what kind of movie, they also have some kind of this design. Okay, now let's look back right here. So what we have, classification. This one I have mentioned, and this deterministic versus stochastic. So the big picture is deterministic and also versus the stochastic. What are about the third one? Discrete versus continuous. I think most of you understand this, discrete versus continuous. Discrete is where the state variable change individually over a time frame, but for continuous, the state variable change continuously, not abruptly over a time frame. So what you can understand something like this, if you have your data, something here, and then something here, and then all of a sudden something here, something right here. So it's not continuous. However, for this one, the change is not abrupt. It's just continuous. You can just put it into, like, it doesn't change too much, and it looks continuous. If you plot the interpolation graph, you can see that it is continuous compared to this one. And like discrete is more towards stochastic, and continuous is more towards deterministic. All right, now the cumulative example, the cumulative interest rate for a personal or for a car loan or mortgage, and also any kind of loan, can be calculated yearly over a period of 10 years or monthly over a period of 10 years. So what does it mean by this? You can calculate the loan yearly for a period of 10 years or monthly for 10 years. So what are the difference? The difference, this one is monthly and this one is yearly. So you are given a period, let's say this is from 1 to 10, and the same thing, this is yearly. And this one is the same thing. So we have 10, 1, 2, 3. Let's assume this is 10, so yearly. But if you have, this is 1 to 10 years, and let's see, 1 year, and then we have 10 times 120 years at 20 months. So you can see that this is more. This is if you go to this one monthly, this, even though this one is the period of the time is the same, but this one you take every month, for every month. So the data might look something like this, more discrete. Then, for example, this case, if you put the in yearly, it can be something a pretty smooth compared to this one. If you take a smaller steps. So this is like you take a smaller step, and this one is take a larger step. Okay, what time is it? All right, 10 more minutes, and then we can take a break. Okay, the types and structures of modeling. So we have 4 types. You can also have some textbooks say 6, some 5, and I can summarize into 4 types of equation. I have summarized into 4 types of equations of mathematical modeling. Number 1, you can have dynamical system. So the dynamical system, I think we have also course on that. Statistical equation, statistic kind of equation. Differential equation also, and also game theory. And I think most of you are familiar with this too. And my field is about the differential equation. And if you have differential equation, of course you need to know how to integrate. Okay, what does it mean by the dynamical system? So the dynamical system is an equation or a function that describes time dependence of a point in a space. So that point is based on time, dependent on time. So therefore, it talks about the temporal evolution of a system. So something that evolves all the time. And the state of dynamical system at an instant time, at that time, is described by a point in n-dimensional space called the state space. So this is quite, for example, if I have, let me take the last point and then we can give you an example. For example, as time passes, the point moves, sweeping out in a curve in the state space called trajectory. Okay, so mathematically speaking, the curve is the solution of the governing equation. So let me give you a simple example. Let's say we have our solar system. Okay, and this is Earth, something like that. So let's assume that Earth is just a point in space. Okay, and the Earth is moving revolving around this sun. So it's moving and then it's dependent on time. So until 1 year and then it complete the system. Okay, so this motion is one example of dynamical system. And this elliptical line is the trajectory of the system. That is one example. Another one, you can also have one-dimensional space. Let's say this one, one-dimensional space. Let's say this is 0, 1, 2, 3, -1, -2, -3. So let's say we have an ant at the small thing, and this ant lives in one-dimensional space. So this ant is just can go forward and can go backward. So the motion of this ant is the trajectory, where it goes, the sweeping of this curve. So, and you can also have two-dimensional dynamical system where you have a y, positive axis, and -1, 1, something like that. So therefore, these ends can go right here. It can go right here. So this thing can move after some time. So that is also the system. So, but this is more random. The trajectory might be random, but you get the point. Okay. These second types of equation. So before this, usually we call it as parametric curves. We have something like this, f that is depend on t, something like that. So usually we call it parametric curve. Okay. A relationship between one or more random variables and also non-random variables. Statistical usually represent data generating process, and unless specified, most of all statistical models are stochastic. That I told you just now. Because why? Because we use probability distribution function in order to modeling, use the stochastic modeling. Okay. One more on variables. You can understand. Differential equation. Yeah, I think you can understand this differential equation. This is used in many fields of applied physical science to describe the dynamic aspect of the system. What does it mean by dynamics? Dynamics, that is something that is always moving with force. And typical variable is time. You can also have space if you have more than one variable, x, y, or z. Geometrical variable can be considered, like I said, x, y, or z. We have two types of differential equation. One is ordinary differential equation, and you can also have partial differential equation. If you have partial differential equation, you can also do some change of variables to make it into ordinary differential equation. So it depends on what kind of problem that you are going to solve. Game theory can also be a part of differential equation. So this is a strategic interaction between two or more rivals, parties, players, and so on. For example, cop and thieves, two parties, government parties, opposition parties. That is also the relationship between enemy, something that is fighting to somebody, or you can also have some company, something that is trying to help the other group and so on. So you can be something that is opposing to two things that are opposed to each other, or you can also have two things that are helping each other. This is the game theory. The situation contains set of rules and also outcomes. What does it mean by rules and outcome? We'll see next time. And it is used to predict the action or the outcomes of the cooperative or competitive parties. So for example, let me give you the current situation in Ukraine and Russia. You can see that Ukraine and Russia are at war right now. So what you can understand is that Russia without Ukraine can survive, but Ukraine without Russia cannot survive, even though they didn't have a war. Because why? Because Ukraine depend on NASA. You can see the history about that. But that is the point. That is the set of rules. So when you see the set of rules, now you can translate into mathematical modeling. You can translate that that situation into mathematical equation, and then after that you can use mathematical modeling. Okay, the last one. I think this is the structure of equation. You can have linear versus non-linear. Linear versus non-linear. I think you can understand that notion. For example, what kind of non-linear differential equation, what kind of linear partial differential equation, and what happens if you put non-linear partial differential equation. It's going to be quite complicated. Explicit versus implicit, and so on. So this one, structure of equation, comprises all these kind of types of equations. So you can have game theory can be nonlinear, game theory can be linear. Game theory can also be differential equation, it can also be partial differential equation. And statistical, it can be linear, it can be nonlinear, and so on. Okay, let's see an example. Okay, so as you can see that this one is linear. Okay, this is linear. Summation that's just a x times y, x times y. And this one is also linear. This one is non-linear, because we have function multiplied by its derivative. Function of that variable multiplied by its derivative. So that is going to be non-linear. Okay, I think you can take a break, and then we'll continue at 6:05. So take a break and then we continue. Okay, so let's come back. Sometimes we need to make our life be simple, and sometimes we need to consider several things to decide. So you can be complicated, or you can just be something that is not complicated. And it also depends on your goal and nature of the model. So it depends on your goal. You can't say everything should be stochastic, everything should be statistic. No, you cannot also say everything has already, the physical theory has already established, and then therefore I don't need any kind of stochastic modeling. That is also not. So you cannot say that one model one model is superior to the other kind of model. So you cannot say that. Each model, each types of, or each classification of mathematical modeling has its own advantages. So it depends on the nature and it depends on your goal. Okay, so for example, so you can see how complicated this is. This is a Navier-Stokes equation, the equation for fluid flow. You have continuity equation, one continuity equation. This is the conservative variables. Mass, so this means that the mass is conserved. And this one are, these three equations are momentum equation. You can see that the momentum of the variables are conserved, and also you have energy conservation, which says that energy can change, but it cannot be destroyed. So energy is also conserved. So you have three kinds of conservation. So you can see how complicated this is. You can also reduce some of these terms by assuming something, and then you can have a quite simple equation. Okay, so example, if you have a Burger equation, this one is Burger's equation, and consider a white noise in a viscous. So because this is due to viscosity, and this is due to the white noise. That is example. And you can also make some assumption. You can say that there's no white noise. You can ignore, and this equation is implicit, and therefore you can reduce this. You can say there's no change in the noise, so there's no perturbation, and there's no viscosity. This is implicit. That is 0, so you can have a simple du partial u partial t plus u partial x equals to 0. So this is, you can see that how easy that is compared to this one. All right, now let's look at another equation. So this is a system of equation. We are going to learn about this. We are going to learn about modeling of this kind of equations in week 7 or 8, in the later week. In week, not 7, week 9 or 10, something like that. Okay. You have this kind of equation, ax equals to b, or you can also have something like this. Security guard can run 1 kilometer. So this is an equation for system equation. Can 1 kilometer in 6 minutes, and a thief can run 1 kilometer in 8 minutes. So if the guards need 1 minute to listen to a report, how long and how far the thief will be caught. So this is also a kind of modeling. So you need to translate this into equation, into variables, and then make it into mathematical equation, and then change it into mathematical modeling. I don't want to solve this, just give you some ideas. Okay, now another example of system of equations. When we have this is called finite element method. I'm not sure if you heard about this, but this is but I suppose that you heard about finite difference method. Okay, that is system of equation. And you can also have the third kind of equation, finite volume method. All right, so this is an example of finite element method. So there are 3 kinds of numerical method. Find these 3, and this is finite elements. So Why we use finite elements? Because usually finite elements is used for solid equation, solid dynamics, motion in solid physical stuff, solid methods. For example, in cars, in structural building, and so on. And what happens if you have a crack right here? If you have crack right here versus what happens if you have a crack right here. So it's going to be give you a different example, a different answer if you for a different crack position. And you can assemble this into finite element method, and then it's going to give you a system of differential equation. So just for your information, this is called the force matrix, and this is the stiffness matrix, and this is your change matrix, variables. So there is like F equals to Kx, F equals to MA, and so on. Okay. And you can also have other kind of equations, such as exponential growth, supply and demand, interest rate, logistic, and so on. So just to give you an overview, exponential growth, you can also have exponential decay. So this is usually related to the population. An example is Malaysia population. For example, you have population is increased exponentially, and then after something happen, it can also decrease exponentially as well. Usually, the decay is related to some chemistry topic, which is the carbon dating. C14, I think it's C14, yeah. Carbon dating, and also bacteria or virus, disease or something. Supply demand, this is from the economic point of view. The supply demand curve, you can have this. More people are asking, the more it will be supplied. This is non-linear kind of curve, or you can say figure, something like this. You can also have a linear supply and also the demand curve, something like that. So it depends on your kind of problems. It's going to be linear or non-linear. Interest rate can also be exponential, related to the exponential growth. Logistic equation can also be related to the exponential growth, but this is more if you have something that is called carrying capacity. For example, if you put some people in a country, that population of the people is going to grow, and somehow people are going to die. It doesn't always growing. So the death and the birth can be related to the logistic modeling. And what kind of logistic modeling? Based on the exponential population growth. And so on. You can have so many, but we cannot discuss all of them. We can discuss only the most important stuff, what we are going to use in most cases. Okay, any questions so far? So basically,
No.
what we do is what we are doing right now is just telling you what kind of let me see. just screen recap of our class today. One is we talk about the classification of modeling. Why we do modeling, you don't have to remember that, you don't have to memorize that, but you need to understand why we use modeling. That's why I didn't focus on that, but you need to know the classification of modeling. The main part of modeling, let me give that right here. Let me just recap what we did, is this one. Classification of modeling. The main thing is either you want to use a deterministic approach or you want to use stochastic approach. It depends on your nature of the problem. Usually, if you are looking for, the nature of your problem is about economic, economic, human factors that you cannot reach or you cannot grasp with your hands, usually you can do a stochastic modeling. But for anything that is applied physical science, usually we use deterministic approach, this deterministic approach of mathematical modeling. For example, how much does it take? How much time does it take for a car that is moving 100 km per hour, and if that car is going to brake, how long does it take to brake if it sees some obstruction and so on? So that is called the braking distance, by the way. So that's why you study when you study the driving license, you're study to take the driving license. You know that you need to count 101, 102 within some distance to the other car at the front of you. So that is the rules. Why? Because it based on that deterministic modeling approach. So two big things, deterministic or modeling. And you cannot say one is better than the other. You cannot say that. You cannot say deterministic is better than stochastic or stochastic is better than deterministic approach. And you can also have a hybrid of those approach. What does it mean by hybrid? It means that you want to focus, if you're focusing on a small scale, you can use deterministic or individual or 1 point or something. So you use deterministic. But if your subject study is huge, for example, I think last time I heard some people is trying to do some disease on dengue in Malaysia or maybe in Indonesia, maybe you cannot take deterministic approach. You need to take a stochastic approach in that case. Okay. Another example is also, for example, gas flow in two-phase gas flow for a different kind of density. You cannot use deterministic, but you use stochastic. There are two approaches. You can use, you don't want to use deterministic, but you want to use stochastic. That is also acceptable. So it depends on the nature of your problem. And also, the next thing that is important in our lesson today is this one, the types of equation. So whatever that I said just now from 5 o'clock until now. So this is the next thing, the second thing that is important in mathematical modeling. It is the type of equation, because it will determine whether or not you can solve, or whether or not what kind of variables that you want, what kind of how many numbers or variables that you want to solve, or how many variables that are interacting with each other. So dynamical system, statistical, or differential equation. And last thing, this is this one. This one. Structure of your equation. the structure of your equation. Is it going to be linear? Is it going to be non-linear? If you have a differential equation, is it going to be an ordinary differential equation, or is it going to be a partial differential equation? Is it going to be implicit, or is it going to be explicit? So it depends on this one. So this one actually based on, so if you are, even though you have stochastic, you don't have any prior knowledge of that, but you can build this kind of equation, linear or non-linear or differential equation, based on your data taken from your empirical study. So from that stochastic study, you create your data and then you create the formula, create the mathematical modeling based on that data. Okay, so just remember 3 things. And all right, now let's look at, I think we can finish at 7. I'm going to give you a leniency for our first lesson. Okay, let me see my lecture number. Lecture number 2. Aku tak ada dalam saya punya ni. Kejap saya nak cari lecture number 2 kat sini. Okay, so tadi just an introduction of modeling. So the next part is the methods of modeling. What are the elementary method of modeling? So this is part number 1. Okay, in this topic, apa ni kita nak tahu apa these 3 things, the elementary method. One is you need to know the terms and definition yang kita nak guna dalam modeling method. And the elementary method, apa maksud terms and definition kat situ. And then we need to develop some connection between variables. For example, what is the connection between space and time? What kind of connection? Changing in space and the change in time will produce a velocity. So that is the connection. The space changes, the times change, and it will create a velocity. And after that, you are going to make some assumption. So for example, if you're talking about velocity, it is going to be different about speed, because if you go left or you go right, the value is going to be the same. But for velocity, the value is not going to be the same. It might be negative, but for speed, there's no negative in value. Okay. So this is just explanation for what we did just now. Mathematical model visualization is a visualization of real world problems. So you can visualize in the mathematical model. It is never a completely accurate interpretation. It's never accurate. Any model has limitation, and good model provide variable results and conclusion. Any models. What does it mean by any models? You can have stochastic, like I said just now. You can have 2 kind of classification of model, either stochastic or deterministic, either ordinary. You are going to use ordinary or the partial differential equation. Every model has limitation. It's not going to be perfect. But the best model is when the result is variable and you can make a firm conclusion based on your model. So mathematical model is to construct and design the real study work behavior of interest. For example, the climate change, the spread of disease, mechanical failure. Climate change, I think you can understand what happened if you increase 1 degree of Celsius in the Arctic. What's going to happen to the whole
Sorry,
world?
Doctor.
Yeah.
The shared screen instead of the first lecture.
Oh, ya ke? Oh, okay. Okay. Yang ni nampak? Yang ni dah okay?
Alright, dah.
Alright, thank you. Okay, so let me just rephrase. Mathematical construction. We need to construct mathematically the design in order to study the real world system or behavior of interest. What does it mean by behavior of interest? Example, mentioned here, climate change. What happened to the change of the other country if the Arctic temperature is increased by only 1 degree? What's gonna happen? And the spread of disease, like what happened just now, the COVID-19 pandemic, mechanical failure. For example, what happened if you change a small screw? Only the difference is just maybe 1 mm, but that screw is smaller than the original screw. What's going to happen to the aircraft during flight and so on? You can also search about this. If you search about JAL 123, you can see that because the mechanic, the aircraft mechanic changed the size of that person replaced a different screw. It caused a disaster for that airplane, JAL 123. Okay, and also mathematical model, it helps us to understand the behavior, and you can also predict something in the future. Okay, now the cycle of mathematical model. First of all, you always start with a real problem. Usually we start with real problem. You didn't start with nothing, because this is what you want to understand. This is what you want to predict what's going to happen. And then you simplify. How do we simplify first? By number one, you identify the variables involved. Okay, you identify the variables involved, and then number two, you make assumption. Without assumption, you cannot simplify. For example, you can understand this if you have a ball, and this ball is moving this way. Can we go to the left? This way. Okay. There are two situations for this ball to move. So let's say this is a soccer ball. Moving this way. This ball, it can move just by this type, or you can also say this ball move this way and also it's rolling. You can have that kind of situation. So that is two different things. So this is a moment and also a motion, but this one is also only a motion to the right. So it's going to be a different. So you do identify the variables, make assumption by removing unimportant variables. The most easy example is the f, which is depend on x and t. If you have a function f, which is depend on x and t. Why? You can also have more complicated. You can have something function that depends on x, y, and t. You can also have something that is depend of x, y, z, and t. So why go for complicated things when you can start with a more simplified things, more simplified equation? So start with simple. Just assume there's no variation in that direction, and the variation is only in x direction. So just consider this one. And after that, so see, this is the simplification. So you say fx depends on x and t only. And then you do the modeling. After you do the modeling, you analyze. And then you make some mathematical conclusion, interpret the model, and you predict or explain, and then go back to the real problem. This is an example of Laplace switch. Laplace switch is something that it's not actually some kind of which, but people interpret it as this because you can predict something when you have a prior knowledge of something. If you have a prior knowledge, then you know what's going to happen in the future. A simple example, weather forecast. It's not always true, but in most cases it is true. Because why? Because you have prior knowledge. It's not like it's coming out of blue, something like that. Okay, what is simplification? So we are talking about this one, simplify. Most model, it simplify the reality. It cannot take every factor into the equation. And model, it approximates real world behavior. It just approximates. The key point right here, simplify and approximate. It's never the real thing. It can be close, but not real. So simplification requires relationship between variables, and this relationship is called proportionality. Okay, like I said just now, if you have a change in space with respect to the change in time, so with respect to change in time, we are calling about the change. So that is called the proportionality. Okay, what does it mean by proportionality? The definition is two variables, x and y, are proportion to each other if one is always a constant multiplier of the other. So one is always a constant multiplier. Y equals to kx. So k is a constant. It can be negative. It can be a negative or less than 1, but it cannot be 0, because if it's 0, then it's not proportion to y, is no longer proportion to each other. It doesn't change with the change of x. So what we write is that y is proportion to x. The change in x is the change in y with some constant. So this is called direct proportionality. So this is directly proportional. But if you have y, I think you understand this, y is like that, that is going to be inversely proportional. So x is decreasing, but y is increasing. So indirect, inverse proportional. In this case, x is increasing, y is also increasing. But this case, if x is decreasing, y is increasing. So inverse. All right. Now, let me give you an example, a simple example of spring mass system. All right. What you can do right here, let's say you have no prior knowledge of this system. Let's say this is a stochastic modeling. Okay, you want to see the value of the K constant. You want to see the value of the spring constant. And you put a mass right here, this is at free, and then you put a mass, and this is going to be at displacement for D. D right here is stand for the displacement. So it will displace by amount of D. And then this is the elongation. And then if you put the mass 50, it doesn't say 50 what right here, 50 something, maybe 50 gram. The elongation is 1. And if you increase by twice, if you increase it twice, this is almost twice, 1.8, it's almost twice, but not exactly twice. If you put triple, and you can see that. So it looks like it is directly proportional. The spring, the weight, when you increase the weight, it increases proportionally. Okay, and then after that, you can see that the slope looks like this. If you plot this equation, this is like a straight line, a linear line. So you can see this one, elongation F equals to, if you plot this one, and you can give, this is your modeling. This is your mathematical equation of this model. So in that case, for example, if I don't have a really big mass, I can predict that if I have, this is 500 until what value? 550. Let's say I want to predict for 1000 of mass, maybe the value is going to be right here. So there is a simple prediction from mathematical modeling. You take the data and then give an equation. Okay, I don't want to go to this one. Okay, and there are also a case where at some point, this spring is going to stretch. Okay, by our physical understanding, something is not always elastic. A spring is not always elastic. It has to be a breaking point where the spring doesn't go back to its original form. So for example, in this case, if I remove M, it's going to be this form. But if I put M beyond its capacity, and finally, it's going to be a straight line. Let's say this is M critical. Okay, it's going to be a straight line because this is too burden for this spring to hold it anymore. And then at some point, if you increase, it's going to be a failure in this one. So let's say M critical 1. Let's say this is the M critical number 2. So M critical number 1 is where the spring is stretched to a straight line, and then M critical number 2, the second critical mass will break the spring. Okay, so what happened by this, if you know the critical value of this, now you can understand that you cannot put the value right here as 1000. The mass should be 1000. You cannot put, because you know that if it's 1000, it is beyond the critical mass. So you cannot put this one. Or maybe what you can say, at some point, when you do something like this, at some point this is wrong, it will go back, something like that, because it is where it reaches its maximum elongation. You can understand. And after this, it's going to be a breaking point. What is my question? After this, it's going to be a breaking point. So it will stop until that one. Just to give you an example of proportionality. Okay. Okay, now the first thing that we need to understand for mathematical modeling is proportionality. Proportionality check the relationship between two variables only so far. I don't want to go to the more than two variables. So what happens if we change x to y? What happens if we can we change y and see what happened to x? No, you cannot do that, because in this case we are talking about the change in input to the output. So in this case, x is the input. X is the input, and see what happened to the output. So what we can summarize in this case, we need to summarize the change in something, the change in the predicted value. So future value means that the current value, the present value, plus the change. Therefore, the change is just rearrange this equation, and then you can see the value of change. So the value of C is future minus the current. You can also understand something like this. Let's say I have x of n plus 1. So this is equals to x of n plus delta x. I can understand that from. So the change is x equals to the current x, and is the subscript for time, plus the change equals to future value. Right? And after that, we get the trend of that change, and we collect some data and plot it. Because while in this case, you might not have prior knowledge. If you have a data, you cannot immediately create equation from that data. No, because you don't know the trend of the trajectory of the behavior of the system. You need to plot the data that you get first, and then see the pattern. From that pattern, you can say, okay, this is going to be linear modeling. This is going to be non-linear modeling, something like that. And you can see. All right, now, if the behavior is taking place over a discrete time period, you can use a difference equation. You can say that this is a difference equation. But if the behavior is taking over a continuous time, you call it as differential equation. So the difference is just for difference equation, and differential equation is the discrete time of period in this case. You can understand this in terms of, for example, I can say what happened if delta t versus dt. Okay, in this case, this is the discrete, this is the continuous. This is the discrete, this is continuous. So continuous is more like when you take a delta t quite small, goes to 0. All right, I think I can stop this one, because the next two part is going to be much more calculation. Okay, any questions so far? Tak ada, sebab saya rasa mudah je. Untuk permulaan saya rasa mudah, sebab so before remember that this cycle of mathematical model, we want to simplify our equation first. So remember, we want to simplify our equation first by, number one, identify the variable involved, and then second thing is you need to make assumption. Okay, so the variables involved, the relationship between the variables are called proportionality. Proportionality is when you have a change in the input variables and you see the change in the output variables. You put something and see the changes. You put something and then see the changes. You cannot see the change without inserting something yet. So you cannot say something without seeing the input first. So that is the key in this second lecture. Okay, so simplification, proportionality, modeling the change, that is. And first of all, we are going to talk about difference equation first. And after that, we are going to talk about differential equation. So for simple modeling, we talk about difference equation. And this is also a basic modeling for any other complicated modeling. We start with difference equation. All right, if there is no solution, then I think I can stop right here because I don't want to go on and during the first class, I don't like too much stuff in my first class, and also I think also first class is not good to have too much. Okay. All right, thank you everyone. So see you on next Monday at 5 o'clock.
Thank you, Dr.